Okay, for our second hour here, we're going to shift gears quite a bit, and we're going to be starting out looking at ratios. A ratio is nothing more than a comparison of two different numbers. For example, I might look at students that are in the classroom with me and students that are on the network. There are 4 students in the classroom for this course, and there are 16 students registered on the network. So I could write that like this, as 4 over 16 is a fraction. I could write it 4 to 16 like that in words, or I could write it as 4 with a colon 16. The two most common notations are the fraction notation and the colon. I prefer the fraction notation because written in that form, there are a lot of things I can do with a ratio that are very, very similar to what I do with a fraction. Now, before I look at that, I want to talk about this here a little bit, why this notation isn't so popular, because that notation only applies in certain situations. A ratio can do two things. It can compare two unrelated numbers. For example, the example I used, 4 students registered at Rice Lake to 16 total students registered at the other locations. The first number was not part of the second number, so I could use the word 2. But what if I said that there are 20 students in the class and 4 of them are registered at Rice Lake? That is now 4 out of 20. So I have to have a different wordage in there, different descriptors in there. It's no longer 4 to 16 because the 4 is included within the other number. So it's now 4 out of 20. In the fraction form or the colon form, it's not necessary to worry about that relationship. So in the fraction form and in the colon form as well, I can reduce this just like I would as a fraction. 4 and 16 both divide by 4. So instead of saying 4 to 16, I can say that there's a 1 to 4 relationship. For every 1 student in Rice Lake, there are 4 students on the network. I could look at the tables in my room here, and it looks like the tables in your rooms are approximately the same size. These tables have a width of 18 inches and a length of 72 inches. I can reduce those like fractions. I'm going to divide this out. First of all, the inches can divide out, cancel out, and both of these divide by 18. So once again, I get a 1 to 4 ratio. Now, couple of things I want to point out here about the first 2 examples. Now, I realize it came out to 1 to 4 both times, and that was maybe poor planning on my part. But you'll notice in both cases, what we compared to each other had the same label. This was students and students. There was something that separated them because there was students at Rice Lake and students on the network, but they were still students. Down here, this was inches to inches. Again, one was inches of width and the other was inches of length, but they were still inches. And that is one qualification of a ratio, is it must compare numbers with the same label. The other consequence of that is the ratio itself, once formed, has no label, no units. This is 1 to 4. This was 1 to 4. So this one here, even though we're dealing with lengths, it doesn't matter. There's no units to it. It's still 1 to 4. You might ask, well, what units do we need to put in there if we're going to compare? It doesn't matter. On that table, no matter what the unit is, for every 1 unit of width, there are 4 of those units of length. It doesn't matter if it's 1 centimeter of width. For every 1 centimeter of width, there's 4 centimeters of length. Or if it's feet, every 1 foot of width, there's 4 feet of length. Or inches, like we used. In fact, if I were to measure that in feet, it'd be 1.5 feet to 6 feet. That still reduces to 1 to 4. No matter what units we use to measure the length and width, we're going to get that same ratio. So what if I have something like 2 feet compared to 18 inches? Well, I can't, that's not a ratio the way it's written. But fortunately, I can change 2 feet to be 24 inches. Now it's 24 inches to 18 inches. Now it's a ratio. The inches cancel out. Both 24 and 18 can be reduced by dividing by 6, giving me a 4 to 3 ratio. Now there's something called a unit ratio. Right now, I left my denominators, the bottom number in each of my ratios, as whatever it reduced to, and left it at that. A unit ratio wants a denominator of 1. So the bottom number equals 1. So for this, I would divide both of those by whatever the denominator is, which is 3. I'd divide by 3 and I'd get 1 1/3 to 1. That would be a unit ratio. Now with ratios, we generally don't worry about it so much as being to 1. There are certain applications where, like a compression ratio or whatever is 6 to 1 or 7 to 1, things like that. But for most ratios, it's okay to leave that as whatever number turns up in the denominator. So what if we have two numbers that cannot be changed to be the same? For example, let's say we go on a road trip and we're going to drive 365 miles. It takes us 7 hours. There is no way we can change miles into hours or hours into miles. So this is not a ratio. This is what is called a rate. The first big difference between a ratio and a rate is what we saw. Ratios compare two things with the same labels or same names. A rate can compare two things with different labels, different units. The second is a ratio is a rate is almost always expressed as a unit rate. In fact, I can't think of a case where you would not want it as a unit rate. So what that means here is the bottom number is a 7, so I'm going to divide by 7. So 365 divided by 7 is like 52.1428571 approximately miles over 1 hour. Now, of course, I probably want to round that to 52.14. And once it's in a unit rate, I don't need to leave it in fraction form like that. So what I do is I kind of hide the fraction in the units. 52.14 miles over 1 hour becomes 52.14 miles per hour. You can see the fraction just ends up in the units of that rate. But when you see that, you still need to think that this is what it really means. In fact, sometimes we hide the fraction altogether. We might list something as 24 mpg. What does mpg stand for? Miles per gallon. When you see that, you need to realize that that means 24 miles per 1 gallon. This is the form we need it in to calculate with it. So there are all sorts of rates and ratios out there that we're going to be working with. For ratios, most of it's going to be like mixing ratios. Like you might have 300 milliliters of saline to 120 milliliters of medication. I'm going to just start using it now. The generic term we'll use in here for medication is the word serum. So we can create, there's actually four ratios that can be created here, but we could have the serum to saline ratio. So that is 120 milliliters over 300 milliliters. Those same units, so the milliliters cancel out. Both 120 and 300 can be reduced by dividing by 60. So 120 divided by 60 is 2. 300 divided by 60 is 5, so 2/5. Another ratio we could get out of this would be the serum total volume ratio. So our serum is still 120 milliliters. What's our total volume? 300 plus 120, right? 420 milliliters. Still milliliters cancel. Still both divide by 60. You get a 2 out of 7 ratio. Now as I look at these two ratios, can you see a relationship between them? Both of them are listing serum on top, right? So the 2's are interchangeable. Both have the 2 on top. The difference is one is listing just saline on bottom. The other one is listing total volume. Remember, the total volume contains both the serum and the saline. So down here to get the 7, what you're basically doing is taking the 2 and the 5 and adding them together to get that. So that's total parts. So the other ratio we could have, I'm really sorry about the noise, folks. The other ratio we could have is the saline to total. Now, rather than listing out the actual volumes, we know saline would be 300 over the total of 420. But rather than reducing that, we can pick that ratio out of these other ratios. What number out of these two ratios, what number represents the saline? Five, right? Represents the saline. That's after we reduce the 300. What number represents the total volume? 7, good. So if we reduce this here, we would get 5 over 7. But you can see we can actually get it from the other ratios. So let's say I have a ratio of serum to total volume of 1 to 6. Find the ratio of saline to total volume and find the ratio of serum to saline. Just give you a second, see if you can pick those out. So if the 6 parts is the total volume, 1 to 6 serum to total. So if 6 parts total volume, if 1 part is serum, how many parts have to be saline? 5. So the saline to total volume has to be 5 to 6, or 5 out of 6. Well, then the ratio of serum to saline, which of those numbers represents the serum? 1, and saline, 5. Good. Now there are also all sorts of rates that we're going to deal with. Rates that you'll deal with in the medical field especially, you might have milliliters per hour for some of your IV drips, or milliliters per minute even. If you have 8,000 milliliters going over the course of 8 hours, well, that reduces. 8,000 divided by 8 is 1,000 milliliters per hour. Notice again, since this is a rate, the fraction kind of gets pushed off into the units. So now let's say we know we want an infusion rate of 450 milliliters per hour. You need this to last for 8 hours. What we can do with our rates, remember our rates are really a fraction. 450 milliliters per hour is really 450 milliliters over 1 hour. We want to know how much this is going to be for 8 hours. Now we're looking at this. This looks like fractions, and it is. One way we could go about this is ask ourselves, well, 1 hour times what makes 8? Well, 1 hour times 8 hours makes 8. So the top up here would have to be multiplied by 8 as well. So 450 times 8 is 3,600 milliliters. Well, not all of these relationships work out quite that nicely. For most of our rates it does, because the denominator in the rate is always a 1 if it's a unit rate. But for some of our ratios it might not. For example, let's say that we have a 2 to 7 ratio of serum total volume. And we want to know how much serum is it going to take to create 200 milliliters of solution. Well, what do you multiply 7 by to make 200? Well, that's not so simple, is it? To find that, you just take the 200 and divide by 7. Now, once we get that number, what are we going to do with it? Well, that's the number that we would multiply by here to get 200, so we're going to have to do the same on top. There's going to be 2 times that number. Now, there's a reason why I didn't do any calculating yet. I just wrote that out. So we're going to take the 2 here, and we're going to multiply it by 200 divided by 7. 200 divided by 7. This is the basis for a process that most of you have probably seen before, called cross multiply and divide. So 2 times 200, you notice the 2 and the 200 are diagonal from each other. You will multiply the two numbers that are on the same diagonal. 2 times 200 is 400. And then you will divide by the number that's on the other diagonal by itself. Divided by 7. That will give us 57.142857 approximately. So 57.14 milliliters of serum would be required to create 200 milliliters of total solution. Make sense? What I just did there was a shortcut. That whole idea, cross multiply and divide, works. I mean, we did it with our percents as well. But it really is a shortcut. There's a longer process to it that looks like this. Here we're missing the x, so we are going to cross multiply. The 3 and the 30 are diagonal to each other. But technically, we should multiply the other diagonal as well. 5 times x, which is 5x. And the way the math works is those two diagonals must be equal, those diagonal products. So the 5x must equal 3 times 30 is 90. So we can divide by 5 to get that x must equal 18. And that would be equivalent. Those would be equivalent fractions if I put 18 in here for x. The reason I'm showing you this is we don't always have simple little proportions like this where one of the whole sections is the missing number. We could have something like this. Six over x plus 5 equals 18 over 30. Here, if I just tried to cross multiply and divide, it's not going to work so well because this isn't just x, it's x plus 5. So we can just cross multiply here. 6 times 30 is 180. So that's our product on that diagonal. Going this way, x plus 5 times 18, well, that's 18 times x plus 5. We're going to distribute. So that's going to equal, actually I'll rewrite it down here. We know those two have to be equal. 180 has to equal the 18 times x plus 5. So we're going to distribute the 18. 18 times x is 18x. 18 times 5 is a positive 90. And now we can solve. Subtract 90. 180 minus 90 is 90. Equals 18x. And then divide by 18. So 5 equals x. Now we saw these proportions working in our percents before. Let's just take a quick review of those. For example, let's say that in a given month, for the month, there were 820 critical patients. Of those, 369 survived. Find the survival percentage. So, we're looking for a percent, which is always out of 100. The percent that would be going up here would be the survival percentage is what we're looking at. So that is survival. So those are the ones that survive. The 100, of course, when we're talking about percents, 100 always represents the total. So this is like we were talking before. What goes on the other side has to represent the same things. Survivors were 369. Total was 820. So we can cross multiply and divide here. 100 times 369 divided by 820 is 45 out of 100, or 45%. There's a 45% survival rate. Let's say there is 15 milliliters, or there are 15 milliliters of medication, of serum, and 120 milliliters of solution. Find the concentration. So again, the concentration is a percent. Blank out of 100 equals, remember the percent, the concentration represents the amount of serum, and the 100 represents the total volume. So on the other side here, 15 milliliters of serum, so the 15 milliliters goes on top. 120 milliliters total solution, 120 milliliters goes on bottom. So cross multiply. 100 times 15 divided by 120 gives you 12.5. That's 12.5%. Any questions? Okay. Last thing we have to deal with. We saw this a little bit. I want to do a quick review of powers. X to the third times x to the ninth. Do you remember what that becomes? X to the, careful, 12. Remember, when multiplying variables, you add the powers. If I had x to the second times x to the fifth, remember x to the second is 2 x's multiplied together. X to the fifth is 5 x's multiplied together. If I'm multiplying them all together, I now have 7 x's multiplied together. So when I'm multiplying, I add the powers. X to the fifth divided by x to the second would be x to the third. Remember, x to the fifth on top is 5 x's. X squared on bottom is 2 x's. I'm canceling out, and I'm left with 3 x's on top, or x to the third. When I'm dividing, I subtract the powers. 5 minus 2 makes 3. X to the third to the fourth power is going to be x to the 12th. This is x to the third times x to the third times x to the third times x to the third. 4 of them. That's 3, 6, 9, 12. X to the 12th. When we're taking a variable with a power to another power, you multiply the powers. 3 times 4 makes 12. Why am I reviewing this? Well, because we're going to take another look at our place values and apply it in a little bit different way. Actually, another thing we should look at here, what is x to the power of 0? Careful. 1. Anything to the power of 0 is 1. What's x to the power of negative 2? It's 1 over x squared. If we look at things, let's say I have 5 to the power of 3. That's 125. 5 squared is 25. 5 to the 1 is 5. You see here that every time I reduce this power by 1, this result is divided by 5. So if I keep going, 5 to the 0, dividing by 5, that has to be 1. 5 to the negative 1, well, 1 divided by 5 has to be 1/5. 5 to the negative 2, dividing by 5, 1/5 divided by 5 has to be 1/25. And 5 to the negative 3 has to be 1 over 125. You see here that there's a connection. 5 to the negative third is the reciprocal of 5 to the third. 5 to the negative 2 is the reciprocal of 5 squared. So 5 to the negative 6 is just going to be 1 over 5 to the 6th. Okay, so now, why am I so concerned with that? Well, let's look at our place values again. This is the ones place. tens place, hundreds place, 1,000, 10,000s, 100,000s, 1 millions, and so on. Going this way, it's the 1/10ths, the 100ths, the 1,000ths, the 10,000ths, and so on. You can see as I move either one spot to the left or one spot to the right, I'm always either multiplying by 10 or dividing by 10. But you can also see here, we have what's called a base 10 numbering system, a decimal numbering system. What base 10 means is our place values are actually exponents with a base number of 10. You can see very easy, this is 10 to the 1, 10 to the 2nd, 10 to the 3rd, 10 to the 4th, 10 to the 5th, 10 to the 6th, and so on. 1 would be 10 to the power of 0. This is 10 to the power of -1, 10 to the -2, 10 to the -3, 10 to the -4, and so on. The reason I'm listing out the place values like this is we may want to abbreviate numbers. Sometimes we can abbreviate a number like, let's say I have 3,900,000. I will sometimes abbreviate that as 3.9 million. Well, rather than writing out the word million, another way we could have abbreviated that was to say 3.9, and the millions place value is the 10 to the 6. 3.9 times 10 to the 6. And that's where our scientific notation comes from. If I want to write a number in scientific notation, I write it so that there's only one digit in front of the decimal point, and then I name the place value of that digit. So let's say that we have 82,000 here. Well, my first digit is the 8. This is 8.2. Then I have to name the digit, the place value of that digit that's in front of my decimal point. This is why there's only ever one digit in front of the decimal point in scientific notation, is the power of 10 is naming the place value of that one digit that's in front of the decimal point. What place value is the 8 in? Here. The 10,000 or the 10 to the 4th. So it's 8.2 times 10 to the 4th. So this 10 to the 4th is saying this 8 is in the 10,000ths place. If I have 0.0091, that's going to be 9.1. What place value is the 9 in? 10 to the -3. You can see that really small numbers are in the negative powers of 10, and our large numbers are in the positive powers of 10. In fact, something larger than 1 has to be in the positive power. Something smaller than 1 has to be in the negative powers. Now, we don't want to have to draw out our place values every time we convert numbers. So let's take a look at a pattern here. The 3.9 million, or 3.9 times 10 to the 6th, when that started out, the decimal point was at its end, and it ended up here. It moved 1, 2, 3, 4, 5, 6 places. Notice our power of 10 was 6. 3,900,000 is a large number, so that's a positive power of 10. For our 0.0091, the decimal point started here and had to move to here. It went 1, 2, 3 spots. Notice there's a 3 in my power of 10. Now 0.0091 is a very small number, so it is a negative power of 10. It's in the negative place values. So we can remember the positive or negative just by where the place values are on our place value chart. But we don't actually have to draw it out. We can look at something like 270,000. Okay, the decimal point is here. We want it here, so it's 2.7. How many places did it move? 1, 2, 3, 4, 5, right? Is it going to be a positive 5 or a negative 5? Positive, because this is a large number. So we have 0.00053. Now the decimal point starting here, we're going to want it to go there. So it's 5.3 times 10 to the, well, how many places did the decimal point move? 4. Good. Is that a large number or a small number? It's a small number. So this is negative 4. So if I have 7.4 times 10 to the negative 5. First of all, I know, is this going to be a big number or a small number? Small number. So 7.4, I'm going to have zeros in front of it here most likely. How many places does my decimal point have to move? 5 places to make it smaller. So my decimal point starts out here. It has to go to the left to make this number smaller. Well, I can move one spot to get past the 7. There's no other digit, so I have to fill in zeros. There's 2, 3, 4, 5. So that becomes 0.00074. Likewise, 1.6 times 10 to the 4th. Is this going to be a large number or a small number? Large number. So my decimal point is going to be moving that way. How many places? 4. So I go 1, gets me past the 6. But again, I have to add zeros. 2, 3, 4. That is 16,000. So I'm going to leave the converting at that. You'll practice that in the homework. I want to look a little bit at operations with these. We're not going to get too deep into that in here, but I do want you to see it a little bit. If you do your chemistry class, you might have to operate with scientific notation. So anyway, let's take addition and subtraction again. Remember our rules for addition and subtraction. First rule, 1, is you need the same name. Well, the same name in numbers comes right down to the place value. You can only combine digits that have the same place value. Tens, hundreds, thousands, whatever. In our scientific notation, place value is indicated by that power of 10. So to add or subtract, they must have the same power of 10. Then, of course, the second thing is you combine counts and you keep the same name. So if I were to add 3.5 times 10 to the 6th, I'm putting it in parentheses just to show that's a single number, plus 4.9 times 10 to the 6th. First of all, I can add these because they have the same name. They're both 10 to the 6th. I'm going to combine my count. 3.5 plus 4.9 is 8.4 times 10 to the what? Well, when I add, I keep the same name, so it's going to stay 10 to the 6th. When I multiply or divide, one, I do not need the same name. And second, I'm going to combine the counts. But I'm also going to combine the names. So I might have 3.2 times 10 to the 7th times 6.5 times 10 to the 5th. Those don't have the same names, but it does not matter. When I multiply, I don't need the same name. So I do 3.2 times 6.5. I'm going to combine the counts, which is going to give me what? 20.8. 20.8. But then I also, when I multiply, I also have to combine the names. So 10 to the 7th times 10 to the 5th. What's that going to become? When I'm multiplying exponents with the same base, what do I do with the powers? Add them. 7 plus 5 is 12. That's times 10 to the 12th. Now there's a slight issue with this answer right now. Can anybody tell me what it is? There's 2 digits in front of the decimal point. I only want, for scientific notation, I only want 1 digit in front of the decimal point. Because the power of 10 is supposed to tell me the place value of my digit in front of the decimal point. There's 2 digits there right now. So which one is that power of 10 describing? So I need to move my decimal point to make this 2.08. But when I move my decimal point, I have to adjust the power on the 10. Did this number, when I went from 20 to 2, did it get larger or smaller? It got smaller, right? Went from 20 down to 2. If the number gets smaller, the power has to get larger. So the number got smaller by 1 decimal place, by 1 place. The power has to get larger by 1. So 12 plus 1 is 13. 20.8 times 10 to the 13th. If I'm dividing, actually do this, 728 times 10 to the 5th divided by 2.4 times 10 to the 12th. Do I need the same name? No. Multiplying and dividing don't need the same name. So I am going to divide 1.728 divided by 2.4, which is going to give us 0.72, correct? But I'm also going to divide the names. What's 10 to the 5th divided by 10 to the 12th? When I divide exponents with the same base, what do I do to the powers? Subtract. So 5 minus 12 is -7. That's 10 to the -7th. Now there's a problem here. There's a 0 is the only number in front of the decimal point. I want 1 digit in front of the decimal point, and I really don't want it to be 0. So I'm going to change this to be 7.2. Now this time, I went from 0.7 up to 7. So this number got larger by 1 decimal place. Right? So what has to happen to my power? It has to get smaller. So I'm going to subtract 1. What's -7 minus 1? Careful. -8. So 7.2 times 10 to the -8. Any questions? So now I'm going to go back to subtraction for just a second. (8.37) times 10 to the 13th minus 7.86 times 10. Now this has to have the same name, so I'm going to give it 10 to the 13th as well. Because when I add or subtract, I can only combine things that have the same name. So I'll subtract 8.37 minus 7.86 is 0.51 times 10 to the what power? 13th. When I add or subtract, I keep the same name. So that's going to stay 13. Now, what do I want to do with this? I want to make it 5.1. That number gets smaller or larger. Well, 0.5 to 5 is larger, isn't it? So my power has to get smaller. What is 13 minus 1? 12. So 10 to the 12th. Okay, so for homework, for what we covered today, we covered again, I know I gave you this one last time, but we went over this again. 53 to page 53 to 54. 1 through 15 is your mixture problems. Page 60 to 61. 1 through 47 and 61 through 65, the odds. This is solving more complex equations with fractions. We didn't do a lot of that, but take a look at them. If you have questions, we'll answer them next time. Page 67 through 68. 1 through 27, the odds. This is given a formula, putting, like we did with the body mass index and temperature, putting the numbers in for the variables and doing your order of operations. Page 73, 1 through 39, the odds. That's your ratios and proportions. Page 78, 1 through 35, the odds. That's just a review of percentages, of percents. And finally, oops, 2 more. Page 84, 1 through 31, the odd. And page 87 through 88, 1 through 39, the odds. That is the powers and then working with scientific notation. So that's a lot of pages, but remember that top one that just went off the screen, 53 to 54, was one from last week. You just want to make sure you look them over and see if you have them down. I am anticipating I'm probably still going to have to answer some questions on the mixture problems next week yet. So don't feel bad if you're still having a couple of road bumps with them. With that, I'll let you guys out of here. You have a great week. We'll see you next Friday. 2 weeks from today, by the way, is our next test, just so you're prepared.